Welcome to our class. We continue with the deployment and verification of Noir generated contracts on base Sepolia. Now, this is the end of this series of lessons. We've been doing it end to end from the day we began. So in our next class, we'll be looking at then how do we deploy and verify on scroll Sepolia. Now, so in our today's lesson will be, first of all, we look at how to write a circuit in Noir, generate proof, generate solidity contract. So this is a verifier.sol. Then after that, we will deploy the verifier.sol to base Sepolia. And of course, before deploying the Sepolia, we'll have to acquire free ETH in our account, MetaMask account. So again, I'll be taking you through those steps. So as I've said, one of the things we'll be doing is circuit generation, writing the circuit. Under that, proof knowledge of two secret scalars X and Y, such that their product is 42. So these are zero knowledge proof, where the product will be known to both the prover and to the verifier, but the secret scalars are only known to the prover. So we'll be looking at how do we write such a circuit. And then after that, how do we generate a proof using BB? And then how do we convert the proofs and the public inputs to on-chain encodings, and then deploy and verify solidity verifier using Foundry, and then to interact by calling verify proof. So the objectives in our lesson 1, you must understand how to the circuit logic and constraints work, how to run and interpret the provided unit tests. Of course, we'll write unit tests just to ensure that our circuit is working as required, that our main function is correctly written. Then produce a proof and format it for on-chain verification, and deploy a verifier contract with the Foundry to base Sepolia. And then you must also know how to verify the proofs using Explorer or using CIL, and then apply secure practices for keys. Of course, this one is using the e.env, the environment, be setting up the environment for deployment. So these are part of the objectives that we're supposed to achieve by the end of our lesson today. Now, before we write the circuit, the overview, want to write a ZK proof for multiplication and addition. So supposing you have two scalars X and Y, whose product is 42 and their sum is also known. So the sum is known. The question is, can we ensure that X and Y remains private so that only the prover knows what they are and the verifier does not? So if that happens, then the circuit will be said to be zero knowledge proof, so that the verifier is not able to gain any knowledge other than knowing that the prover knows what X and Y are. So our circuit will look like this, our main.nr. So you just open a new project and you paste this code in the main.nr. Now, when you look at our main.nr, you realize that X here is private and Y is also private, but the outcome is public. The outcome is public. And so we assert that their product is 42 and then compute their sum. Compute their sum. So this sum is the output. This is what the verifier knows. So the verifier is given the sum. We are not giving this product to the verifier. Our output is what we give to the verifier, and the output is our sum. So this is what the verifier will get to know from the prover. And then, so the verifier will just confirm that the prover knows what X and Y are. Also, you know how to create a project in your WSL. I'll just again remind those who are joining the class for the first time, although we've been doing this for a long time. You can always visit one of our lessons we did earlier to just learn how do you write a circuit in Noir. But in your WSL terminal, you would make a directory, and the name of the directory, for instance, what do we call this? We call it ZK. They just give it a name, ZK for multiplication and addition, or a sum. After that, press enter, then CD ZK, this project, you just want to get inside multiplication and sum. So you CD that. Once you CD that, make a directory circuits, and then press enter. After you press enter for that, you would again get inside the circuits, CD circuits. Then inside the CD circuits, you can nago inish. This is the same steps you've been doing. The same steps you've been doing is this. Now, so nago inish. So this generates. You get a message that you've successfully created a project. That the project has been successfully created. So your project that has been created now has SRC, has Nago, and inside SRC has main.nr. So that main.nr has a circuit, one that comes automatically. So that is the one you're going to replace with the one I've just shared. But before we go there, you've just done nago inish. So you'll now get out of circuits. You're still inside we are still inside our WSL terminal. So CD, then 2 dots, getting out of circuits. Once you get inside you get inside the root, that was ZK multiplication sum. Once you get inside this, you would say code some space dot, then press enter. This one opens for you VS Code, where you'll now go to edit your circuit as I had already explained. So once the VS Code opens, you can do this practically. Of course, I'm not doing it because it's something we've done before and several times. Just trying to do this just for the sake of those who may be joining for the first time. But of course, we also advised them that you can get any of our lessons we did earlier on writing Noir circuits. We've done several of them just to learn how that is done. So once you get inside main.nr, replace the circuit with this. Replace your circuit with this. Now, once you've done that, you can do Nago compile as we always do, just to be sure that it runs properly, it compiles properly. You can also add tests. This is just a sample of tests I've added, but you can add several just to ensure that you test several functionalities and do Nago tests to see if they all pass. So you do Nago test in your terminal. That's what I've said here, that use Nago test or Nago build, depending on your Noir toolchain version. Both positive and negative tests are crucial to ensure that constraints behave as intended in our main. Now, so your project structure, our structure is supposed to be in this form. This is the title. This is the title. And then we're supposed to have circuits here. Let me just add it. Supposed to have circuits. Inside the circuits, we have SRS. Inside SRS, you have main.nr. And this is where we just edited the code that was originally there, changed it, replaced it by the one I've just shared. You'd have targets. When you did Nago compile, of course, you had a few things inside your target, and some will always come in as we proceed. So target will be used to build and proof artifacts. So this will contain our proof artifacts. Even the referred sol will originally be here before we move it to the contract. So the other folder we have is this JS, and this is what will be helping us generate the proofs. It helps us generate proofs. And then we have the contract, a folder, and this is where we will have Foundry projects generating our Foundry projects here. And this is again where we'll be having our contracts, solidity verifier. Then lastly, we have the README. Now, you can go to my GitHub and clone this repo. This repo is in my GitHub, and you see what is under JS, what is under contract, and what I have in my README, what is under that. And of course, this repo, we looked at it earlier, but now we're just using it for deployment in our today's lesson. It's just for deployment, but it's a repo that we had learned earlier when we were writing zero knowledge proofs in Noir. Uh, I've noted here that we are supposed to keep proof artifacts in our target and separate our circuit from verifier code for clarity. And so that is why I've noted that although our verified soul will be generated inside our target, we'll later on move it to our contract, just to ensure that we separate the two. Now, I'd already explained about how we're going to run our tests. You can do Nago build. This is to build the circuit and compile constraints, or we can also do, after Nago build, you can do Nago test just to run the circuit unity tests. If there is any trouble or if there is any error, if the tests fail when you do Nago test, then you may want to inspect the assertion and intermediate witness values. Just check if the assertion is fulfilled as is required. Then ensure that Noir and Barentenberg versions are compatible with your project. You can always install the most current versions. Now, proof generation, when we did this lesson earlier, we had two ways of doing this. And one of the ways was through CLI, while using Noir plus Bartenberg, using the BB command. So this would generate witness and proof artifacts with their binaries. That is one way. And the other way we did generate proof was in our folder.js using yarn generate proof, yarn generate proof. So that is another way we did generate a proof. And of course, we'll still use the same method. Remember, today's lesson mostly is just, I remind you how to do generation of the proof, how to write the circuit, but the most target is how do we then deploy our verifier.sol to base Sepolia, and how do we then interact with it while on chain. So these are the things like writing circuits and proofs, generating proofs is just a reminder that we have our target to deploy the Solidity contract. Now, again, just as a reminder, as I've mentioned earlier about proof generation, here are the commands that we used earlier to do this. Can you generate witness using this command nago execute. Nago execute. And remember, for you to run nago execute, you must have prover.toml. You'd already discussed that. But now the bb command that generates the proof is this bb proof. And this proof is supposed to be stored inside our target. And for us to get it, we are using the witness, which is already inside target. When we did nago execute, we got a witness. And this witness is what we now use to get our proof. And then the proof has to be stored inside our target. So remember, for you to get a proof, then a witness has to come first. So when you go to your, after running this command in your terminal, when you go to your target, you should be seeing this output. You should be seeing some proof, which is in binary. That means when you click on it, it could be telling you that it cannot open. And then apart from this, you'll also be having public inputs inside your target. So when you go to your target, those are the things we've just generated. Now, the other option of generating a proof, I said, is using the JS yarn generate proof. So you would first of all install yarn. First of all, install yarn. Then after installation, you would say yarn generate proof. And you're doing this inside JS folder in your terminal, VS terminal. Now, so your VS terminal will be having several folders. And again, I said you can go to my GitHub, clone this repo, and then you see what folders are inside JS that are assisting us in the generation of the proof at this stage. This generation of the proofs, you can do it manually, or you can also automate it so that you have scripts that would do the generation of the proof and even a compilation automatically. Now, after generating the proof, you remember we're supposed to interact with it later after deploying our contract. And I've already said that the proof generated that is inside our target currently is binary. That means you cannot read it. But the one that we will want to interact with our contract is supposed to be in hexa. It's supposed to be in hexa. So the next thing after you generate this proof, the next thing is to convert it to hex. So, because that is what we will require later to interact with our contract on chain. So I've said here that the on-chain verifier expects the proof as a single hex bytes, and the public inputs are also supposed to be hex. Of course, public inputs, we have no problem because what we currently have is already in hex. So there's no problem, but the problem is on the proof. It's in binary. So to convert our proof to hex, I've given you the command here, but you have to go to the target, not target, circuit. Our circuit folder is where our target is. So inside that, in your terminal, you can run this command. So this command gives you your proof in hex. Now you can also make this proof in hex as a single line. So for you to do that, again, there's a command I've given you here. You may want to inspect to see whether the proof that you've just now converted is indeed in hex. So if you want to do that, then you would again use this command. This command is able to give you this proof in your terminal, and you can see that it's indeed in hex and it's a single line. So that is what we will now go with. Of course, it has been saved also in your target. So when you check your target again, you will see it there. This is what we'll move with to our on-chain to do interaction with our deployed contract. Now, the public inputs, I'd already said, we also require it in hex, and again, we'll require them to, at the time of interacting with our deployed contract. Now, we can now look at the verifier contract, which, as I alluded earlier, when we generate it, it's supposed to be in target, but then we're supposed to move it to contract. So I've said most ZK toolchains produce verifier contracts for Solidity compatible with the Ethereum virtual machine. And the workflow is generate the verifier Solidity artifacts via BB or Noir backend, add the verifier contract, add it to the contract. So you move it to contract. Okay, so you can move it contract under SRS, but in what I've been doing, I have not been moving it to SRS. I've just been moving it directly to contract, so that I'd not have a folder called SRS. I'd not have a folder named SRS in my contract folder. So I just have contract, and then inside contract, I have verifier.sol. So this one is not part of what I have, but in most cases, most contracts you see people be having this SRS, and then inside you would have a verifier.sol. Now, after getting the verifier.sol, we would then use Foundry's Forge to deploy it and auto-verify on the explorers. So that means, therefore, we're supposed to install Foundry. And to install Foundry, inside your terminal, you can run this curl, this. And this gives you the most current version of Foundry. After you give it some time, after it runs, then you can also run Foundry. After that, you can now verify the version and maybe cast version if it's possible. But what I'm interested with at this point is Forge version. You can find out what your Forge version is. Of course, I'm just using it as a means of confirming that my Foundry has been well installed. It will come with the Foundry.toml, and this Foundry.toml will later on add a few things like the optimizer settings, just ensure that our contract is of the size that can be deployed. Is of the size that can be deployed. Otherwise, normally the contract that is generated by Noir is of larger size, more than what can be deployed. So just to ensure that it's of better size, so good size, you add optimizer settings. So these are the optimizer, only these two commands here. You add this. Then after that, you can, you want to run Foundry tests. You place the verifier and helper contract under contract. I've already said that. I've already said that in my working, I do not require SRS inside the contract. But this one I can, it's there. You can also add scripts, as another folder inside the contract, you can have scripts. Now you cd contract and then run this. This is just as I already said, you already have a contract, but you want to ensure that it's of the right size that can be deployed. So this validates the verifier contract locally and catches obvious encoding mismatches before deploying. That is what it does. Now, so about circuits, about writing the circuit and then the proof generation and then solidity verifier, we are done with that. In fact, we've generated the proof and converted it to hex, because I said what we'll use to verify our deployed contract to interact with it on chain would be the hex proof, not just this binary proof we produced earlier. Now, so we are done with that bit. So the bit that we are now to proceed to is how do we get our best Sepolia in our MetaMask account? Because it's not there on MetaMask, best Sepolia is not there by default. So you can create it. But if yours already has it, and then there's no problem. But if you don't have it, then you can create it, and this is the chain ID, and this will be the public RPS, and this would be Explorer. And in our previous lesson, I taught you how to create this network, the Sepolia network. And you can create another network that you may want, so long as you have the right chain ID, you have the right public RPC, and the right Explorer. Once you have the right ones, then you can always create any network you want. Now, so apart from creating this network, the Sepolia network, the other thing we want is to learn then how do we obtain free base Sepolia ETH. How do you get that? And then we'll also learn on how to MetaMask setup, and that is what I've been talking about, then faucets and bridging small amounts to base mainnet when required. Of course, it will be required to have a small amount in base mainnet so that you can acquire free ETH in base Sepolia. You cannot acquire free ETH in base Sepolia if your base mainnet doesn't have some small amount like 0.001 ETH. So it should have something for you to get the free ETH. So that means we will again go through how do you bridge small amounts to base mainnet. And then after that, now how do we get the free ETH in base Sepolia? Because this free ETH is what we'll be using in our testnet to do our testing, deployment, and so on. We are not using real ETH. Now, so we are at our MetaMask stage. We want to add the Sepolia network, and here are the steps. So, of course, MetaMask is always as an extension in our Chrome or in our browser. So once you click on it, that extension, go to settings, then go to network, add the network. Then at that, you can now fill what I said, that once you have them, you can add any network. So where there's network name, just add base Sepolia. Where there is RPC URL, add this, chain ID, then currency is ETH, then block explorer, here is what you add. Then you can save and switch to base Sepolia. Remember we said when you're doing our testing, we'll be using private key, and it must be private key to an account that it does not have real ETH. So we've just gotten an account that has no real ETH. And so this account, we add this network, base Sepolia network. Of course, by default, you have base mainnet. The only thing we will change there is the RPC URL. That's the only thing we'll change, but the rest will remain as it is. Now, the other things we require are faucets for base Sepolia. So the common faucets are the Alchemy faucet. And here is the link. And this is the one I'll stick to. I'll use the Alchemy faucet going forward just to get our URL. But you can use any other. Some faucets check your base mainnet balance. So consider bridging a small amount if you are blocked. So I'd already said this. This is just again for emphasis. So update base mainnet RPC in MetaMask if present. So MetaMask sometimes uses Wallet Connect RPC for base mainnet, but the same chain ID. But now when it uses this Wallet Connect RPC, this one, if you're trying to bridge, it will not go through, it will fail. So for you to ensure that you're bridging the small amount to your base mainnet succeeds, you would fix it this way. You would go to MetaMask, settings, networks, base. So the chain is correct. But now, once you reach base, just click on edit. There is those three dots, right click, and you'll see edit. And then to edit, we're only editing at one point. The others are correct. So the RPC URL is what we are editing. You change it to this. and save. Maybe I can show you this. So this is what I'm referring to. My MetaMask extension is here. Of course, it asks for password. Okay, I'm going to the account that I'm using, that I normally use for this lesson. So this is where we have popular networks. And it's here that you're looking for base, So this is base. And I've claimed that the RPC that is here is not correct. So when you when you click here, there's edit. And what you come and change is this. The RPC URL is already changed. So just click here, add RPC URL, and then replace with what we have. But the rest remains as they are. The rest remain as they are. Once you're done with that, you can click here, save. So you just change that RPC URL, replace it with this. This is the correct one. Now you can now bridge a small amount to base mainnet. And for me, what I'm doing is I have an account that has already ETH, and I have this that it doesn't have. So the one that I have ETH in is my Ethereum mainnet. And I've opened another account. So I want to transfer from this account A to account B. Remember that in account A, I have my real ETH in Ethereum mainnet. So I send it to account B. It will, of course, go to Ethereum mainnet of account B. And I want it to get into base mainnet. And I think you're getting the difference. You're getting what I'm explaining. I'm saying that I have account A and account B. My account A has a real ETH and account B has 0 ETH. And I'm supposed to, for me to get free ETH in my base Sepolia, the requirement is that my main Sepolia should have some ETH, 0.001 ETH. Now, my account A has real ETH in Ethereum mainnet. So I send it to account B and it goes to Ethereum mainnet of account B. From this Ethereum mainnet of account B, I want it to proceed to base mainnet. So that is now what I'm explaining here. That's what I'm explaining. I'm saying bridge small amount to base mainnet. So I've just, it's already in my Ethereum mainnet. It's already in Ethereum mainnet, and I want it to go to base mainnet. That is what I'm explaining here. And the small amount is just 0.001 ETH. So I would visit this. When you click on this, and then connect your MetaMask, and then there is from and to. So you choose from Ethereum mainnet to base mainnet. Then the small amount that you want to move, and then click deposit. Now you can confirm by going to your accounts to see whether the transaction has been successful in your accounts. You can now go to your accounts and just confirm. Something that is almost immediate, but you can wait for a few minutes sometimes, but it's immediate. So of course I know that you know how to send ETH from the Ethereum mainnet of account A to Ethereum mainnet of account B. So there is no problem here. The only problem was now how do we get this from Ethereum mainnet to base mainnet? That was our issue. And it's what I've just explained. Now we have RPC providers and testing options. One, we can have, you can use this, or you can use any other. There are several that you can use. Now, once you've done this, you now have really you now have real ETH in your base mainnet. You proceed and get, and this is what I was asking, what I was talking about. You proceed and get the free ETH in your base Sepolia. Okay. Now this part for testing connection would come later after we have updated our .env. Yes, that is when you're setting an environment for deployment. You're setting an environment for deployment, we will come back to this part. And it's what I'm now explaining here. You want to set environment, so .env, you create, this is a file you create inside the contract.env, and you add your your secrets. For instance, you add your RPC URL, you add your private key that you're getting from MetaMask account, and you add Etherscan API key. This will be using them for deployment. This one is used for, the Etherscan is used for verification. But these other two are used for deployment of your contract. So for deployment, you require these two. And for verification, you need to add this other one. Now, this is not the only thing that should be in your .env. You should also ensure that your .env is not going to GitHub if you try to commit it to GitHub. If you try to commit your repo to GitHub, ensure that your .env does not go there. It goes to gitignore. And that's what I've said, security here. We don't want it to get to GitHub because it already has your private key. And the private key, if anybody gets to have it, then that person has exposure to your ETH. In case your account has any ETH, this person will have an exposure to your ETH, can get access to it. Now, so we've just talked about this environment. Now, I want to show you how to get each of these things we added to our .env. How do we get our RPC? How do we get your PK, private key? And how do we get our Etherscan API? So that is what I want to take you through. I'll begin by getting the private key. Begin by getting the private key. So I'll just again share my browser. I go to my MetaMask. What I want is a private key. So I'll come to these three horizontal lines. Click on these three horizontal lines and you can see account details. Click on account details and you can see network, private keys. Yeah, we are interested in the private key. So when you click on it, you are asked to enter your password. Asked to enter your password. Then confirm. And there is something here. It says, don't share your private key. Don't share your private key. I'm surprised that this format is exposing all the private keys, is unlike the one I was doing earlier. I don't know how this happened. Let's just go back. Let's go back and see. I was not expecting that because the last time when we did it, we did not get that. Last time that was not the option. I think it just changed today or what. So we come to network accounts, private keys. Why? It was not coming like that in our previous. I think this is something that I just changed today. It was not the case. I don't know why it's exposing private key for all the accounts so that you can just copy what you want. It was not the case before. So I can see this time, all the private keys are here. Okay, so you copy the private key that you want and go to, we want it in our .env. We want it to be there. So this is the steps. These are the steps I just given you. Go to MetaMask account details, export private key. But I can see that it's a bit different, slightly different when we went to do it hands-on. Now you get your private key and we'll use it to in our .env. There's some warning here that never share or commit private keys. So remember we said that our .env, if you are going to commit your project to your GitHub, then your .env should remain in gtignore, should not go to your GitHub for security reasons. That is why the warning is here. Now, once your environment is well set, and of course, you can always go to our earlier classes and listen to how we set the environment, how we got our RPC, how we got our PK, Etherscan, and so on. Once the environment is well set, you go to your VS Code, and inside your VS Code, go to contract and run this command. So this deploys the verifier.sol. It deploys the verifier.sol. And after deploying, it also verifies. You can see we already have included the Etherscan. Okay, this one has Etherscan here. It's not necessary because our .env already has Etherscan. So you don't require this part here. But if your .env did not have the Etherscan, then this part will be important here. But at this point, our .env has already taken care of this. So you don't require it here. You only require this, this, and then the broadcasts. So you'll just change, replace this with the right link you got for URL, RPC URL, and replace this with the correct private key you got, and then run this in the terminal. Inside the contract folder, inside the contract, get inside the contract and then run this. I have noted that verify triggers Explorer source verification using your API key. Now, the deployment we've done without scripts. You may want to, if you are doing deployment most often, you want to automate it. So to automate it, you will have a script inside the contract folder. You create a file called script. And inside that, you have this, the script will be a folder inside contract. Then the file will be deploy.s.sol. Then this deploy.s.sol, you paste this code. And you'll be using this to deploy most often, if you're doing it most often. So if you have this code inside your deploy.s.sol, you can now do the deployment using this command. And remember I said that this is not necessary because has already been taken care of by our .env. So you only require broadcast at this point. Oh, broadcast is already there. So we only require this, only require this, only require this. So just replace that, replace this, and then you can see we have deploy.s.sol inside. So this is slightly different from the other one because this one we're using the deploy.s.sol script to do the deployment. Now, remember our contract, we've done deployment and verification. So when you go to your on-chain, you will see your contract marked green with a check mark, means it has been verified. You are able to see the Explorer at that point, now the compiler, and so on. There's a lot of information there. You can see read and write contract. You can see all those options. So to interact with it, it means just doing the read contract. And so that is what we'll be doing. When you click on read, you would see it will require you to paste public inputs and then paste the proof. And we had already converted this to hexa when we began our lesson. So the hexa formats are what you then paste inside that space. This part, we have already done this part at the beginning when we were converting our proof and our public inputs to hexa. Now, what are the common issues and how do you fix? One of the common issues would be faucet rejection. So maybe you just want to ensure that the requested base Sepolia ETH, ensure you requested base Sepolia ETH and check if faucet requires base mainnet. So, we had already explained that. They already said that in some cases, for you to get base Sepolia, you would require ETH. For you to get base Sepolia ETH for free, you would require to have some amount in your base mainnet. So that could be an issue, and that is how you